Welcome to video number 18 for Physics 102. This video introduces the idea of calorimetry and phase transitions. Last time in class, we defined what heat is. Heat is the transfer of energy via particle motion. Since heat is a form of energy transfer, the units of heat are joules. We also calculated the amount of heat that was able to flow via a process we called conduction. By the end of this video, you should be able to quantify the temperature change that results from adding or removing a certain amount of heat. You should be able to define both specific heat and heat capacity. You should understand that adding or removing heat does not always result in a change in temperature. Sometimes a phase change is what results. And you should also understand that temperature is constant during a phase change. Calorimetry is the study of the impact of heat transfer. When temperature is far from the melting point or boiling point of some material and I add some heat, what happens? Well, the temperature increases. Mathematically, we would say that we add some heat and we see a change in temperature. This little symbol means proportional to. As the heat increases, so will the change in temperature. If the change in temperature were to decrease, then Q would also drop. Q would be negative in that case. So positive Q means I'm adding heat and the temperature is going up. Negative Q means I'm removing heat and the temperature is going down. So what else can impact the amount of the temperature change for a given amount of heat energy? Well, the more mass there is, the smaller the change in temperature. If I give a certain amount of energy to a small block, it will get hotter than a much larger block of the same material. So, mass is going to be underneath Q. There's also going to be a material-dependent property, which we label with a little case C. Metals, for example, undergo a much larger temperature change for the same amount of energy. Now, typically, this expression is written in a slightly different form. Usually it's written Q equals mc delta T. Now, we just thought about the amount of temperature change for a given amount of heat in terms of mass. But often, it's more convenient to work in moles. So, for mass, we have mc delta T. Whereas, if we were to think about moles, we would not have the mass m, we would have the number of moles in, and instead of the lowercase c, specific heat, we would have the uppercase C, heat capacity. Now, the lowercase c, specific heat, that's used for mass, has the units joules per kilograms Kelvin, while the capital C, heat capacity, has the units joules per mole Kelvin. The specific heat and the heat capacity are going to be related by the molar mass of the substance. Now let's have a quick look at some specific heats and heat capacities for various liquids and solids. We can see some interesting trends in this table. Many elements have about the same heat capacity, about 25 joules per mole Kelvin. We can also see that the specific heat of water is very high. This fact has important implications in everyday life. Moving on to gases, however, things get a little bit trickier, because it turns out that we could measure the specific heat of a gas in one of two ways. We could either measure it in a box, which means the volume is constant, in which case we specify it C sub V, or we could measure it in a balloon, in which case the pressure is constant. We call that C sub P. The result does matter. You get different results whether you measure things in terms of constant volume or in terms of constant pressure. Here's a table for these heat capacities for different gases. We can see some interesting patterns in this table. We see that monatomic gases tend to have CV of approximately 12.47. Diatomic gases seem to all have a similar heat capacity of around 20. And polyatomic gases seem to have a heat capacity somewhere in the neighborhood of the high 20s. So it seems that the structure of the molecule is important for the heat capacity. You also see a quantity gamma in this table. Gamma is just a variable that's defined as the specific heat at constant pressure divided by the heat capacity at constant volume. We will see that this is a handy little variable later when we study a particular type of process with an ideal gas known as an adiabatic process. So, sometimes when we add heat, we get a change in temperature. However, an addition of heat does not always cause a change in temperature. Sometimes the energy goes into causing a phase change instead. What do we mean by a phase change? Well, in order to understand this, we need to understand what the phases of matter are that we're going to consider in this course. There are solids, liquids, and gases. There are other phases of matter, but these phases are not run into very often on Earth, so we're not going to consider them. A phase change is when you go from one phase to another. For example, when you melt a solid or freeze a liquid. Or, if you evaporate a liquid. The reverse process of evaporating a liquid into a gas is known as condensing a gas into a liquid. It's actually also possible to go directly from a solid to a gas. This particular process happens a lot with frozen carbon dioxide at standard temperatures and pressures. The solid carbon dioxide sublimes directly into a gas. The reverse of sublimation is once again condensing. If we think about what happens when we add heat while melting a solid, we see that the energy of the molecular collisions is not going into increasing the kinetic energy, but instead going into breaking the bonds of the solid. Since the kinetic energy is not increasing, the temperature is not increasing. As such, the temperature remains constant during the melting process. Similarly, the temperature would remain constant during an evaporation or a sublimation process. Let's think about this in an example of when we add some heat energy to some cold ice. By cold, I mean the temperature of the ice is below its melting point, so below 0 degrees Celsius. Let's imagine we're adding heat at a constant rate, say 50 watts, or 50 joules per second. And we're going to plot the temperature of the H2O as a function of time. Well, first, we add heat to the ice. The ice is well below its melting point, so it doesn't melt. The temperature of the ice rises, until eventually the ice reaches its melting point of 0 degrees Celsius. The additional heat, 50 watts at this point, does not change the temperature from 0 degrees Celsius. Instead, the temperature remains constant at 0 degrees Celsius. During this interval, we have both ice and water at 0 degrees Celsius. We can turn this statement on its head and say, we know that if we have both ice and water, we know the temperature is 0 degrees Celsius. Once all the water has melted, we continue to add energy, and now the energy goes into raising the temperature of the water. So, how much energy does it take to melt or sublime or evaporate a material? Each material needs a different amount of energy to melt, boil, or sublime a kilogram of it. This amount of energy is based upon the chemical structure of the material. The amount of energy required to melt, boil, or sublimate a kilogram of the material is called its latent heat. Now, there are several different latent heats depending upon the process we're considering. There's the latent heat of vaporization, which is when we're boiling a liquid into a gas or condensing a gas into a liquid. We indicate this latent heat with L sub V for latent heat of vaporization. There's the latent heat of sublimation, and there's the latent heat of fusion, which is the latent heat that comes in when we're either melting a solid or freezing a liquid. What do these latent heats mean? Well, perhaps it's best demonstrated in the context of an example. For water, the latent heat of fusion is 3.35 times 10 to the 4th joules per kilogram, and the latent heat of vaporization is 2.26 times 10 to the 6th joules per kilogram. What this latent heat of vaporization means is that I need 2.26 megajoules to boil 1 kilogram of water. And I need 3.35 times 10 to the 4th joules to melt 1 kilogram of ice. Writing this mathematically, we say Q is equal to plus or minus m L sub x, where x could be vaporization, sublimation, or fusion. What's with the plus or minus? Well, the positive sign is for when we add heat to the system and we get boiling, melting, or sublimation. To get these things, we have to add heat, so positive Q. The negative sign is when we want to condense or freeze a substance. In this case, we have to remove heat, so negative Q. So the sign that you need for this expression depends upon what's going on in your process. This concludes this video. You're going to use these ideas in the future to understand calorimetry problems.